mentioned that he hit his leg and is going to the clinic. Anyways, moving on to this question here. Actually, in terms of molecule, why is it possible to compress a gas but not liquid? I've mentioned this during last week's class. Gas particles are essentially far apart, right? When I compress it, there is literally space in between them to be compressed, whereas liquid molecules are already touching each other in a randomized arrangement, guys. So there's no space in between them. So your answer here should be gas molecules are far apart. There is space between them to be compressed, while liquid molecules are already touching each other. There is no space from them. Something along these lines. Everyone? Hey, I'm going to go a little bit faster in these exercises here. Please stop me if you have any questions. If not, I'm going to assume that you got it correct or you understand, because I want to move on to the next chapter today, which is essentially your Q equals to MC theta formula. Okay. Anyways, moving on. State what happens to the molecule of a gas in a sealed container when the temperature increases. What's going to happen is the pressure is going to increase, right? As you can remember, they gain more. Once they have higher temperature, they'll have higher kinetic energy, right? And if they have higher kinetic energy, they're going to collide against the walls more frequently and produce a greater force per unit area. And thus, this question is similar also, guys. This question is actually quite related to the one on top. First and foremost, I say that the pressure increases. Then after that, you need to state in terms of molecules why the gas pressure increases. Once again, it's because gas molecules gain more energy and collide against the walls more frequently, or they have higher energy and produces a greater force per unit area. Can you guys hear my baby cry, by the way, from the background? No? Really? Okay. Good, because I was afraid that it would disturb you guys. Okay, everyone? Done with this part, Yeah? Moving on to the next part. So in this case here, they're asking you for your Boyle's law formula, right? Because if you look at this question, it says that a helium-filled weather balloon is held at ground level. The volume is this amount, okay? The pressure of the helium is this amount. The balloon is released and rises to a height where the balloon is this new amount. They ask you to calculate the new pressure, right? Assuming the temperature stays constant. So from here, not much you need to do. You just need to remember the Boyle's law formula, which states that P1V1 is equals to P2V2, and literally substitute all the numbers in. 8 is 98 multiplied by 4,800 equals to P2 multiplied by 7,200. If you press that into a calculator, assuming that you know algebra, right, you'll get essentially 65. You'll get 65 kilopascals. Did anyone not get this calculation or not? Good. Suggest why it may be necessary to release helium from the balloon as it rises even higher. Think about it. As the balloon keeps rising higher and higher and higher, right? There is essentially less and less air pressure acting on the balloon. And because there's less and less air pressure acting on the balloon continuously expands, right? It will expand beyond a point where it's about to pop. So if you don't release helium while it rises, it will expand so much that it will eventually pop, right? So you're basically trying to prevent the balloon from bursting or anything along the lines that indicates that it's going to go kaboom. All right, guys. Yes. Please stop me if you have any questions. If not, I'm going to move on. This question here is quite interesting in a sense that if you look at this question here, it says that a student carries out an experiment to find the relationship between pressure and the volume of a gas. From here, our basic understanding is that pressure increases, volume decreases. They are inversely proportional, right? Then they say, the table contains 4 of her sets of measurements at 250, 30, 500, blah, 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 and blah, blah. The trend is that you can see the increasing pressure decreases the volume. And this is where the first question comes in. It says that use the data in the table to suggest the relationship between pressure and volume. Explain how you reach the conclusion. Since the question say use the data, you need to quote the data from the table itself. So my answer will be something like, as the pressure increases from 250 kilopascals to 1000 kilopascals, the volume decreases from 30 cm cubed to 7.6 cm cubed. Their relationship is inversely proportional. Something along those lines. Don't need to write their relationship. They are inversely proportional to each other. Oh, some of you are still copying, is it? Can I? Yeah. Moving on, state the property of the gas apart from the mass that remains constant during the experiment. Guys, you need to understand that pressure, volume, and temperature, they all have chain effects towards each other. Today, if I'm playing with pressure and volume, this must be kept constant. Alternatively, if today I'm playing with pressure and temperature, right, this must be kept constant instead. Okay, because they all have chain reactions towards each other. And because of that, I must mention that temperature. Temperature remains constant. Bang, one, easy. Then after that, in this question here, it's quite straightforward. They give you the lake, which is essentially 5 meters deep and a density of 1000 kgs per meter cube. They ask you to calculate the pressure. What formula should I use again?
Hello?
What formula should I use here to calculate the pressure? Wait, you got to do or not this question?
No, I didn't do this one.
You say you did 2, right? Wow, this is not your second one. Ethan, tell me what formula should I use for pressure?
Rho GH.
Very good. It's essentially just rho GH. Jolie, my friend, rho GH, and then you just substitute everything in 1000 multiplied by 9.8 multiplied by 5. Press that in your calculator. You'll get something. Somewhere around 50,000. Somewhere around 50,000 pascals. Okay. It's just a matter of pressing a calculator. Then this question is very interesting. Let's go through it together. Okay. It says that a bubble of gas escapes from the mud at the bottom of the lake and rises to the surface. Place one tick in each row to indicate what happens to the volume, the mass, and also the density of the gas bubble, assuming no gas or water vapor enter or leaves the balloon. Starting off with the volume, guys. What do you think happens? Will the volume increase, stay the same, or decrease? Hayden. Wait, Hayden. Okay, wait. Is this guy channel? Wait, Hayden, can you hear me or not? Bloody hell. What are you doing? What happens to the volume?
It increases
How come?
because it rises.
It rises, then the volume increases, man. Can you give me a more reasonable answer now? How come when it rises, the volume increase? Junkan, you want to try this or not? How come the volume increases? Do you know?
The volume increase because because when you go up from the bottom, then when you are down there, it is more dense, there's more pressure. When you go more and more up, there's less pressure. Is it because
Yeah, it's not because of the density. It's because as you rise towards the top, the bubble increases in size because it's more pressure here and less pressure here, right? My friends, because there's less pressure here, that's why the volume increases. How about the mass? What happens to the mass? Jolie, what do you think?
Hello?
What happens to the mass?
The mass increases
How come?
because the volume increases.
Volume increase and mass increase on me? Are you sure?
No.
Answer is not. The mass will stay the same because nothing goes in or out. Nothing enters or leaves the bubble. And because of that, I know for a fact that the density will decrease because density is mass over volume. This stays the same, this increase, this will decrease. You understand or not, Wei? For this one here? Anyone don't know what I'm talking about? Very good. Moving on. How many more questions? My God, 2 more. 2 more before I can go on. Figure 5.1 shows a gas contained in a cylinder enclosed by a piston. At first, the length of the gas contained is 100 cm. The pressure of the gas is shown is 300 kPa. Okay. The cross-sectional area is this amount. Describe the motion of molecules of the gas. They are basically moving in random zigzag motion. This one you're basically explaining Brownian motion, guys. The gas molecules will move in, they move in random zigzag motion with random speeds. Your mark here. Right? This is essentially the motion of gas molecules. Then, this question is very commonly asked in your exam. They say use the idea of momentum to explain how the molecules exert a force on the cylinder, which leads back to the general formula for general physics formula, guys. How is momentum related to force? Anyone can remember? How is momentum related to force? Wow, everyone's stunned already. Let's go with some names. Ethan, do you recall or not how momentum is related to force? How the formula momentum is related to force?
Change in momentum is mv minus mu, right?
Wow, very good. Yes. Then,
And that formula is in like to help to calculate impulse,
okay.
which is like
What's the second formula for impulse? One was mv
force and
minus mu.
time.
Very good. Excellent, Ethan. That is the correct answer. I'm genuinely pleased that someone remembers. So basically, guys, momentum related to force is only through this formula, right? I need to explain how the momentum exerts a force on the wall of the container, which for those who do not remember, last week we mentioned this, every time the pressure increases here is due to the force per unit area increase, right? The force per unit area increase is due to the gas molecules constantly colliding against the walls of the container, guys. And that's how you're supposed to relate everything here. But since they want me to relate force with momentum, I need to go one more level. How did this force come to be? The force itself was basically change in momentum over time, right? This change in momentum over time, which is the collision of the molecules against the walls of the container, increases the force per unit area, which will ultimately increase the pressure. Before I go on, anyone don't know what I'm talking about? This question comes out all the time in your exams. If you don't understand this, now is a good time to ask. A good 100% absorption rate. Just what I like. Anyways, they're supposed to say, as the molecules, molecules collide against the wall of the container, this change in momentum per unit time, which increases the force unit area generated on the wall, ultimately increasing the pressure. Please copy this down. This answer is asked. This answer is used all the time. Jolie, finish copying already. Guys, done copying? Ethan, are you done? Okay, good. Moving on to the next question. Guys, this next question here is once again testing your understanding on Boyle's law. Because right now I am given that the piston is moved so that the new length is 40. Initially, it was 100. Right now, I push this piston all the way until it is left with 40 here only. So they ask what's happening in terms of the new pressure. How to do this calculation? What should I do? Start off with the formula first. Jolie, what's the formula? P1V1 equals to P2V2. So right now, how much is my original pressure? Yeah, how much?
300,
How much?
300,
Good, it's 300 and my original volume?
100.
It's not 100, but you can use 100 as the calculation. Because this 100 is just the length of the container and the cross-sectional area is actually 0.12. When we're talking about volume, it's essentially length times area. But since they both have the same area, eventually they'll just cut off each other later on. So we just look into the length. But anyways, it's acceptable. Is equals to your P2 and your V2 will be how much?
I don't know.
Read the question again.
40.
Very good. Press that in your calculator and you'll get your P2 as something, 750 kPa. And once again, they ask you explain in terms of behavior of molecules. Why pressure has changed is once again because with a smaller space, the same amount of air molecules occupy a much smaller space and thus collide against the walls more frequently. I'm going to say as the volume decreases, same amount of air molecule, something along these lines. Okay, guys? Good, moving on to the last question before we move on to the next topic, guys. This question is quite a funny question, lah, not gonna lie. And my students usually struggle to answer the last question here. Is it a figure 4.1 shows small closed transparent chamber containing smoke? The chamber is brightly lit and observed through a microscope. The smoke particles are seen as very small bright dots. Describe the movement of the dots. Once again, you're going to explain Brownian motion, which states that the dots move in random zigzag motion with random speeds. Then bam, you'll get your 2 marks here. Okay, then what is just Brownian motion all the time. Then explain in terms of molecules how this movement is caused. How come they move in random zigzag motions? This is because the molecules constantly collide against other molecules and is bombarded into different directions. And bam, you get your 2 marks again. And finally, the last question here, they say, describe what is seen as the smoke particles move towards and away from the observer. I see most of you guys don't wear glasses here, but have you guys ever did an eye examination before? When you do the eye examination, you see through that hole and then they give you that it's either a hot air balloon or a very small cottage somewhere in the eye. And you know what I'm talking about? Right. No? For those who don't, I don't know how to explain this. It's just, okay, just imagine today, right? You take something that's relatively close to your eye, and then you like move it very close to your eye. You'll see that eventually the image blurs out, right? Which is what's happening here, you know. Describe what is seen as the smoke particles move towards and away from the observer. When the smoke particles move towards you, it will blur out. If it moves away, you can focus on it again. So that's the answer that they are actually looking for. You need to mention that the smoke particles move in and out of focus. And you get your mark already for this one here. Ken? Get everybody? Anyone has any questions? I know my gut feeling tells me that you all have no questions at 100% absorption rate, just the way I like it. Seriously, anyone got any questions or last chance? Anyone want to ask anything with regards to any of the things we've mentioned so far? Good. Moving on to the next part here. This chapter, I think I don't know if I included this or not in your book. The latent heat of fusion and latent heat of vaporization has been removed from physics. It moved to chemistry. So you can ignore this whole part here. I don't know if it's still in there or not, but evaporation is still there. So like latent heat of fusion and latent heat of vaporization, ignore. Okay, let's not waste too much time and let's talk about how heat expands and cold contracts. You've definitely heard of this term before, right, guys? Everyone heard of this, heat expands and cold contracts, right? The first experience I had with heat expanding and cold contracting is, I don't know if you guys did this or not, I was in primary school, but essentially my school teacher had a metal hoop, you know, like a metal ring, and then she had a metal ball. This metal ball, before you heat it up, if you put it through, right, it will hole slide through the whole one. Right. Then after that, the teacher said, look what happens right now. Then she took this metal ball and she started heating up with fire. As she started heating up this with fire, right, what happens is that as she tries to put it back through the metal hoop, the ball no longer goes through. How come? What's happening? Starting with Hayden. What's happening?
The particles expanded.
Okay, correct. But what causes the expansion, Junkan? Do you know?
What caused the expansion? Because they get more energy, so they move further and further apart, is it?
Good. They vibrate further and further apart. Excellent. Guys, listen up. In terms of heat expansions, right? Imagine today this is a normal temperature solid particle. Solid particles, we know that they all vibrate in fixed position, right? Hey, give me 1 minute. I need to do something. Tools, search tools, alternate text. Anyways, back to this here. All right. So everyone knows that the solid particles, they actually vibrate in fixed position. This vibration is forever one, it will never stop, right? So what happens is, right, as I supply heat energy to these molecules here, right, I constantly heat it up, what's going to happen is each and every one of these molecules will have a greater amount of energy. Although their energy is greater and their vibration takes up a larger space, but ultimately they still have not overcome the forces of attraction. That's why they stay as a solid. They'll just vibrate faster. Sorry, they'll vibrate in a larger space and thus taking up a larger space, as you can see here. Okay? But once again, they're still held together due to the strong forces of attraction, as of most solid particles are. Okay? So the keyword is that they gain energy and vibrate at a larger space. So if you look here, when heated, solid, liquids, and gas, they all gain thermal energy. The particles start to move about more, and the vibration takes up more space. So they expand in all directions. The opposite is true as well. If temperature falls, the material will get much smaller. That's why we always have the saying that heat expands and cold contracts. Okay? Liquid will expand more than solids because of their weaker bond. If you think about it, right, the only reason why this thing doesn't expand in a very big volume is because for solid particles, their forces of attraction is very strong, right? But if you compare solid particles versus liquid particles, their forces of attraction is much, much weaker, meaning to say it has a higher tendency to vibrate at a further distance. And of course, gas particles will expand the most when heated, simply because, once again, they have the weakest forces of attraction. You understand what I'm talking about, guys? Anyone has any questions they want to ask for this part here? Good, 100%. Once again, if you look at these diagrams here, you'll see that these are applications of heat expanding and cold contract. Most of the days you'll see, not most of the days, all the time you'll see that your high tension cable will be constructed in a slanted manner. Why? Because if it's hot, right, the tension cable will just expand more and it'll slant even more, right? But when it's cold, especially in winter countries, they'll contract, And as they contract, right, the worst case scenario, they'll contract and become shorter like this. Imagine today I got an idiot engineer, right, who designed the high tension cables, one straight line. He say, save costs. Straight line, less length, and less material needed, so save cost, right? During hot day, no problem. On hot day, it will just expand, right? It will just slack a little bit more. But during the cold day, if it was designed this way, right, the cold will actually contract the cable, and they'll literally pull themselves apart, guys. Do you understand what I'm talking about? Yes, guys. It's the same for metal railway tracks and also airplanes, right? There'll always be a little gap in between, especially the MRT stations, right? Because imagine the train constantly glides past this railway track. It's going to generate a lot of heat, right? And if it generates a lot of heat, this thing is going to expand. But the gap is already taken into account the expansion already. But sometimes shit happens, guys. When shit happens, it's like something like happened in the Japan or Taiwan railway incident. You know what happened, right? So it was a really hot summer day. Then the railway tracks were constantly expanding beyond the gap. And when you keep expanding, eventually something buckles. So like imagine they expand, and then they keep pushing against each other. Eventually something buckles. And when something buckles, the train track becomes like this right now. And guys, this is no funny joke, man. When a train goes like this, I think if I remember correctly, like 50 people, 100 people were injured, and then like a certain amount of people died because of the train 翻车. But yeah, this is a unexpected freak scenario. Even the engineers didn't account for that. But anyways, this is the application for heat expanse and cold contracts. Everyone got a good idea of what's going on, yeah? Yes, good, excellent. Now we talk about how do we prove that solid expands the least and liquid expands more. Okay, a very simple experiment is basically by placing a thermometer, right? You place this thermometer into extremely hot water. It doesn't have to be extreme, actually, even like 100 degrees Celsius is fine. Okay. When you place this thermometer in hot water, right, what happens is, right, the heat, listen up, guys, listen up. The heat, right, will actually cause the glass bulb to expand a little bit more. When the glass bulb expands a little bit more, what happens is, right, the liquid level actually drops a little bit, right? This will happen all the way until the heat penetrates through the glass block and actually starts heating up the liquid. When the liquid is heated, what happens is the liquid will go all the way until it reaches 100 degrees Celsius. From here, you can tell, right? The expansion of glass was this amount. The expansion of liquid was this amount for the same amount of temperature, guys. So that's why if you look at this whole statement here, it kind of makes sense, right? Initially, the indicator drops because the round conical flask expands when heated. It was a solid particle, so the expansion was very little. Later, the heat reaches the red ink and causing it to expand. The indicator rises more because the expansion of liquid is higher than the expansion of solid. Yes, before I proceed on to a very important chapter, everyone don't know what I'm talking about. Wow. Everyone understands what I'm talking about. Good. Moving on. Okay, this part is extremely important, guys. Listen up. If you've been half dreaming all this while, now is a good time to pay attention. Specific capacity is something that will for sure 100% come out. 100% come out in your paper 2 and maybe come out in your paper 4. Okay? You need to be able to understand what specific heat capacity is. If you think about it, guys, different materials all have different specific heat capacities. A very common example is when you drink Milo, right? If you drink Milo, especially if it's hot Milo, you'll usually have a spoon inside that Milo drink, right? Right, then you stir. You pour 100-degree water into the powder and then you stir it up, right? And then once you stir, finish all the powder dissolve already, right? You usually take the spoon out and you let it maybe in the air for like 5 seconds or 10 seconds. You can literally put the spoon onto your tongue and it will not burn you, right? Then you decide to drink the Milo at the exact instance after putting the spoon in your tongue. If you drink the Milo right now, is it still hot or not? It's still hot, right? How come it's still hot? But the spoon not hot already, can put it on your tongue already. How come? Who haven't answered me yet? Hayden, how come?
The drink has more energy than the spoon.
Okay, not exactly wrong. But the question I'm asking for is how come the water remains hot while the spoon cools down already?
Because the spoon you took it out, so like the heat gets out faster.
Not exactly the answer I'm looking for. But let me tell you why, guys. Most of the time, because the spoon is usually made of metal, metals generally have a low specific heat capacity. Let's say this metal spoon, right, has a specific heat capacity of 500 joules per kg degree Celsius. But water or any liquid in that point, liquid generally have extremely high specific heat capacities. Let's say, for example, your Milo powder, your Milo drink has 500 joules per kg degree Celsius of specific capacity. Guys, I want you guys to look at the units. The units actually tell a story, guys. For the spoon, right, you only need 500 joules of energy to be dissipated from the spoon. That is 1 kg, and it will lose 1 degree Celsius. So if let's say the spoon releases 1000 joules, it will decrease temperature by 2 degrees Celsius. If it releases 1500 joules, it will decrease by 3 degrees Celsius and so on. But you look at liquid, guys. Liquid generally have a much higher specific heat capacity. And because it has a much higher specific capacity, it means to say it's very hard to heat up, but very hard to cool down as well. Right now, for the liquid to decrease by 1 degree Celsius, assuming it's 1 kg also, right? I need it to dissipate 5000 joules of energy, 10 times that of a spoon. By the time this thing decreased by 1 degree Celsius, this thing already decreased by 10 degrees Celsius already. Can you guys see? This is important, guys. Look at the units and try to tell yourself the story. Do you all understand what I'm talking about or not? Anyone don't know what I'm talking about? Please voice out now. It's important. Okay? Okay? So that's specific capacity. By definition itself, specific heat capacity of a substance is the amount of energy needed. Like I said just now, right, 500 to 5000 joules, right? to change 1 kg of a substance by 1 degree Celsius. It's the same for aluminium and normal water also. You see, aluminium, I only need 900 joules to decrease by 1 degree Celsius. But for water, I need it to lose 4,200 joules before I can decrease by 1 degree Celsius. So let's say, for example, the question will be something like this, okay? I have water that is 5 kg, and I want it to decrease temperature from 100 degrees Celsius to 90 degrees Celsius. Okay? Calculate the energy it must dissipate for it to reach 90 degrees Celsius. You use the formula Q equals to mc theta. Heat energy, mass, specific capacity, and change in temperature. Right, from here, you're supposed to basically get something like 5 kg multiplied by 4,200 of joules per kg degree Celsius, and the change in temperature is going to be 10 here. If you press this in your calculator, you'll get a number. You'll get 210000. Guys, in order for my water that is 5 kg to decrease from 100 to 90 degrees Celsius, I need to lose 210,000 joules of energy before it reaches 90 degrees Celsius. You understand what I'm talking about? Anyone don't know what I'm talking about? Yes? Now, I just want to mention one more thing before I throw you guys into the questions. In your exam, right? You most likely will forget the units for specific capacity. If you forget the units for specific capacity, how do I use the formula to find out what's the units of specific capacity, Ethan? What should I do?
Like use the units for like mass, heat capacity, and change in temperature.
Close enough. So basically, if you forget the units and you know that the formula is Q equals to mc theta, right? You make C the subject. If you make C the subject from this formula, which is specific capacity, it will be basically Q over m theta, right? From here, you know that Q is basically energy in joules, m is mass in kg, and change in temperature is basically degrees Celsius. That's how I know that the units for specific capacity is joules per kg degree Celsius. With this formula, you can actually bullshit your definition also, because once again, if you look at this formula here, specific heat capacity is the amount of energy needed to change 1 kg of a substance by 1 degree Celsius. And this question always asked in your exam, by the way. You need to know. Okay, guys. Anyone want to ask me anything at all? Good. Copy everything down and attempt the 5 questions at the bottom right now. You'll find that question 1 to 4 is relatively easy to do. You have an option to skip question 5 because realistically that question will not come out in your exam. Just skip question 5. Unless you're feeling adventurous though. Usually less than 10% of the class can do the 5th question. Usually. Do question 1 to 5 right now. Give you guys 10 minutes. Done, everyone. Anyone not done yet with the first 4 questions? Okay, good. Check answers, guys. The first one, do you get this amount? 36160 joules? Yes. The second one, do you get negative 90 degrees Celsius? Oh, I don't see so many hot heads nodding anymore. Oh, how many of you guys got this question correct, by the way?
Oh, question 1, can you write it as 36,000 joules?
Can. 2 significant figures. In fact, it's recommended. I just gave the exact number only. 2 to 3 significant figures is always good practice. Anyways, for question number 2, 90 degrees Celsius, negative 90 degrees Celsius. Oh, Jolie, you got it correct, Huh? Then why didn't you give me like this? Who got this correct?
I didn't see the last part.
Who got this correct? No one got this correct. Oh, Ethan. Good. Basically, you're supposed to. This is a make up belief story, right? But you're basically supposed to remove the amount of energy, right? This amount of energy was removed from the water, right? So with this amount of energy removed, I basically need to know how much is the change in temperature, right? That's why although my formula is Q equals to mc theta, I'll make theta equals to Q over mc, right? In this case here, once I substitute all my numbers in, I'll find that the change in temperature is 125 degrees Celsius, right? The change in temperature is 125 degrees Celsius and it starts off with 35 degrees Celsius, which means to say I have to minus it off, right? to get it to -90 because I'm removing heat. I'm not increasing the temperature. I'm removing the energy. Yes, guys? Okay, can? Anyways, it's -90. For question 3 and 4, it's relatively straightforward as well, and 4,200 joules per kg degree Celsius. Can? Everybody can? Very good. Moving on to the next part here. We'll do the questions later on, but let me just finish up these two things, then we'll end the class today. For electrical energy to heat energy, since we know that the general formula, guys, pay attention, power is equals to energy over time, right? Today, if I want to find energy, it will be essentially power times time. But right now, I'm changing it to heat energy. So it's going to be Q equals to power times time. And since I know that Q equals to mc theta, ultimately the formula becomes mc theta equals to power times time. And this is how we convert electrical energy into heat energy, guys, based on different components. Yeah, everyone, anyone got any questions you don't understand for this part yet? Copy this down. We'll attempt the questions after I finish explaining evaporation so that I can give you guys some homework. So can you just copy this down real quick? Now I want to talk about evaporation. Then we come back to this question here. Done? Yes. Okay, let's talk about the last part before I throw you guys into more and more questions. Let's talk about evaporation. Guys, evaporation is quite a popular question in your IGCSEs. And in terms of evaporation, you have to first know where does evaporation occur. Jolie, where do you think evaporation occurs? Inside the liquid, at the bottom of the liquid, on the surface? Very good. It only occurs on the surface of the liquid. Guys, Junkan, how come only the surface liquids can go through evaporation? What do they absorb?
They absorb the heat from the surface because they are the most top. They are on the surface, is it?
They do absorb energy, but not from the surface. They absorb it from the molecules below here. All right, Hayden, next, what temperature does evaporation occur at?
Any temperature.
Good, evaporation will occur at any temperature, guys. As long as it's a liquid, it will occur at any temperature. And finally, after evaporation, what happens to the temperature of the liquid?
It decreases.
Good. Guys, listen up. For evaporation, right, first and foremost, you think about where it occurs, okay? Evaporation will only occur on the surface of the liquid because these surface molecules, they actually gain energy from the molecules below it, not from the surrounding. A lot of students, they like to tell me from the surrounding, but it's actually from the molecules below it. Once these surface molecules gain enough energy, they'll break their forces of attraction and escape to the surrounding as gas particles. So the more energetic molecules are basically escaping, leaving behind the less energetic molecules. That's why the temperature decreases after evaporation. In fact, if you place a cup of water outside of your door and after you go to sleep, you come out in the morning, you take that cup of water and you drink it, right? It's much colder than it originally was because evaporation consistently occurred throughout the night. And evaporation can happen at any temperature. So, if you look at my statements here, evaporation is essentially a change of state from liquid to gas state. Okay? Evaporation will only occur on the surface and at any temperature. Okay? Boiling will be different. Boiling occurs throughout the liquid and only at boiling point. Quite commonly asked in your exam. Okay? Molecules on the surface absorb heat energy from the molecules below it. And once they gain enough energy, they'll break the forces of attraction and escape to the surrounding as gas particles. Right, anyways, the three factors affecting rate of evaporation is surface area, obviously, temperature, obviously as well, and humidity. What does humidity mean, by the way, Jolie?
The moisture in your air.
Very good. It is basically how wet the air is. In Malaysia, it's considered a very humid country. That's why when you run and sweat, you feel really sticky on your body because the moisture in the air is literally condensed onto your skin. Okay, before I move on, anyone has any questions? Oh, good. 100% absorption rate once again. Finally, the last concept I want to talk about before we end the day is essentially how evaporation helps regulate our body temperature. Imagine this, like today you're running, right? Or you're doing some kind of sports thing, right? You constantly sweat. So let's imagine this is a layer of skin, right? And then when you sweat, you develop all these sweat droplets on the layer of your skin, right? These sweat droplets are constantly absorb energy from the skin below, and they actually release the energy to the surrounding as gas particles. So that's why, right? After you sweat, the whole reason of you sweating is to keep yourself cool, you know. Imagine today you got some kind of disease and you no longer can sweat anymore. You know what's going to happen? Every time you run or do any type of sports, your brain literally goes through the blue screen of death like your computer. You know, like, do you guys know what the blue screen of death is for your computer? Maybe it's a generation thing already. But anyways, when your computer gets too hot, it will automatically shut down to protect its components. It's the same like your brain also. If your body gets too hot, your brain will shut down also to protect your components in your body. Okay, essentially that's how heat stroke comes to be. Okay, so when your body sweats, okay, the skin, when your body is hot, your skin secretes sweat. Energy from beneath the sweat is constantly absorbed, and this cools the body back to normal temperature. Hey guys, anyone has any questions they want to ask? Copy everything down and start attempting all the questions from here, guys, from this part here, the 1, 2, and the 3. Everything else is going to be homework. You are expected to finish the work by next week, where we will continue on the question rotations once again. I'm going to be here for the next 5 minutes. So in case anyone has any questions they want to ask, they can ask. If not, you can just copy everything down and then you can go already. Finish the rest of the work by next week. Hey guys, I'm going to stop class here today.